Good morning, student. Today we'll discuss the inversion of the Z transform. The direct evaluation of the inversion integral, you know that direct evaluation of the inversion integral is defined as x of n is equal to 1 over 2 pi j close integral x of z into z raised to power n minus 1 into dz. So this is one way the to find the inverse Z transform, that is a direct evaluation of the inversion integral. Okay, but this requires understanding of the complex variable thing. But this requires understanding of complex variable theory. So the two alternatives are there. To find the inversion of the Z transform, and the two alternatives for finding the inversion of the Z transform. Okay, so the first method is the method of partial fraction. This method of the partial fraction uses the knowledge of the several basic Z transform pairs and Z transform properties to invert the large class of the Z transforms. Okay, and therefore this approach relies on this approach relies on an important properties of ROC. So this approach lies on the important properties of ROC, the right-handed time signal. So, sorry, a right-sided time signal has an ROC that lies outside of the pole radius. Okay, while there is a left-sided time signal. Left-sided time signal has an ROC that lies inside the pole radius. That lies inside the pole radius. Okay, and the second inversion of Z transform method, second alternative method is the inversion methods method expresses x of Z as a power series in Z raised to power minus 1 of the form of equation x of Z summation n equal to minus infinity to infinity x of n into Z raised to power minus n. So this is the second method, and now we'll go for the partial fraction expansion. How to find the inversion of the Z transform. So in a linear time invariant system, generally has a Z transform that are a rational function of Z raised to power minus 1. Okay, of Z raised to power minus 1. So let us define this x of Z. Let x of Z is equal to bz over az. So this can be further written like this: b0 plus b1 z raised to power minus 1 plus bm into z raised to power minus m. So this m is the highest power of the numerator polynomial, and this a0 plus a1 z raised to power minus 1 plus an into z raised to power minus n. So this is the general form of the equation x of z, and assume that m is less than m. We have to assume that the highest power of the numerator polynomial is less than the highest power of the denominator polynomial. But if this m is less than or equal to n, sorry, if m is greater than or equal to n, see this value should be always less than this value. But sometimes this m is equal to this n value, or sometimes m is greater than n, and then you may use long division method. We may use the long division method to express x of z in terms of the form x of z is equal to summation k equal to 0 to m minus n f k z raised to power minus k plus b bz tilde divided by az. Okay, so this is when m is greater than n, we may use the long division method to express x of z. So in the form, so the numerator polynomial b tilde z b tilde z now has order 1 less than that of denominator polynomial. Okay, now this b tilde z has an order 1 less than that of the denominator polynomial, and that is what we require. This m should be less than n. And now the partial fraction expansion is applied to determine the inverse transform of the to find inversion of the Z transform. So inverse Z transform of the terms in the sum are obtained from the pair. Suppose one is there, this Z transform of this is del of n. So what is the inverse transform of del of n? It is a 1. Okay. And the Z transform terms in the sum are obtained. The Z transform inverse Z the inverse Z transform of the terms in the sum are obtained from the pair the Z transform of the pair is like this. So inverse transform of this simple function is 1, and we have to also use the time shift property. The time shift property. So in some problems, x of z may be expressed as a ratio of the polynomials in z rather than z raised to power minus 1. In this case, we may use the partial fraction expansion method. First, we convert x of z to the ratio of the polynomials in z raised to power minus 1. Okay, and this conversion is accomplished by factoring out the highest power of the z present in the numerator from the numerator polynomials and the terms with the highest power of z present in the denominator as an operations. So this ensures that the remainder has form described by the equation 1. So let us consider, for example, if x of z is equal to 2z square minus 2z plus 10 divided by 3z square minus 6z plus 9. Then we factor z square from the numerator and 3z cube from the denominator, and thus we write therefore x of z is equal to, take outside z square, so in the bracket it will be there 2z raised to power minus 1 plus 10 z raised to power minus 2 divided by 1 by, sorry, divided by, take here 3z square outside, 3z square, sorry, 3z, it is a cube, not square. It is a cube, so take outside here 3z cube. What will remain in the bracket? 1 minus 6 z raised to power minus 2 plus 3 z raised to power minus 3. So what will be there? 1 by 3 z raised to power minus 1 into 2 minus z raised to power minus 1 plus 10 z raised to power minus 2 divided by 1 minus 6 z raised to power minus 2 plus 3 z raised to power minus 3. So in this way, we can factor z square from the numerator and 3z cube from the denominator, and therefore we can write like this. And the partial fraction expansion is applied to the terms in the parenthesis. The partial fraction is applied to these terms which are expressed in parenthesis, and the factor 1 over 3 z raised to power minus 3 is this factor is incorporated later using the time shift property. Okay, in this way we can find the inversion of the Z transform by applying the partial fraction expansion to determine the inverse transform of the B tilde by A. Okay, so the partial fraction expansion which is given by this equation 1 is obtained. This is your equation number 1. So the partial fraction obtained the partial fraction expansion of equation 1 obtained by factoring the denominator polynomial is obtained by factoring the denominator polynomial into the product of first order term. Denominator polynomial into a product of first order terms, and the result is x of z is equal to b0 plus b1 z raised to power minus 1 plus b m z raised to power minus 1 divided by a0 into the product of over k equal to 1 to n of 1 minus dk into z raised to power minus 1. So where these dk are the poles of x of z, where dk is the poles of x of z. If none of the poles are repeated, then use the partial fraction expansion. If none of the poles are repeated, then using partial fraction expansion, rewrite x of z as a sum of the first order terms, as a sum of first order terms. Okay. Therefore, we can write here first order terms x of z is equal to summation k equal to 1 to n k divided by 1 minus dk z raised to power minus 1. So depending on ROC, the inverse Z transform associated with each other, these will be associated with each term and is then determined by using the appropriate transform pair. Okay. So the appropriate transform pair is like this. We have got this A K divided by 1 minus dk z raised to power minus 1. So this is with ROC, magnitude of z is greater than dk. If such is there, then its inverse Laplace transform will be ak, this first term, into dk raised to power n into u of n. Okay, so such term is there with ROC, magnitude of z is greater than dk, then its inverse z transform will be ak, that is a constant in the numerator, into dk raised to power n into u of n. Or suppose ak divided by 1 minus dk into z raised to power minus 1 with ROC, the magnitude of z is less than dk, then its inverse z transform will be minus sign will be there into ak, where ak into dk raised to power n into u of minus n minus 1. Okay, then we can see the effect of the ROC on the inversion of the Z transform. So here, if the ROC is greater than with ROC, the magnitude of Z is greater than dk, then its inverse Z transform will be ak into dk power n into u of n. But if the ROC magnitude of Z is less than dk, then its inverse Z transform will be minus sign ak into dk raised to power n u of minus n minus 1. So in this way, the each term relationship between the ROC associated with x sub z and each pole determines whether the right-sided or left-sided inverse transform is chosen. Okay, in this way we have to find the inversion of the Z transform, and this will be again clear when you discuss the example. Okay, so I think this is thanks for thank you.